AWACS radar works, explained simply. This aircraft can detect objects hundreds of miles away. It can track dozens of targets at the same time, and it builds a real-time picture of the sky that no ground radar can match. But here is the real question. How does it actually do that? Because AWACS does not just see things, it uses physics, signal processing, and smart engineering to turn invisible radio waves into useful information. And once you understand how it works, you will never look at radar the same way again. In this video, we are breaking down how AWACS radar works, step by step, in a simple and clear way. No complex math, no confusing military jargon, just the core ideas that make this system so powerful. If you enjoy content like this, consider subscribing. It helps the channel grow and lets me make more deep dives like this one. Now, let's get into it. What is AWACS? The E3 Sentry is what is called an airborne early warning and control system. Instead of being fixed on the ground like a traditional radar tower, AWACS operates high in the sky at about 9 kilometers altitude. That gives it a massive advantage over ground-based systems. From that height, it can monitor huge areas at once. We're talking about hundreds of kilometers in every direction. But the real power of AWACS is not just where it is located. It's how it uses radar technology to understand what is in the air around it. What is radar? Let us break radar down to its simplest form. Radar sends out a radio signal. That signal travels through the air at the speed of light. When it hits an object, like another aircraft, some of that signal reflects back toward the source. That returning signal is what the radar system detects. So, in a very simple way, radar is like sending out a question into the sky and listening very carefully for the answer. The word radar itself comes from radio detection and ranging. That's exactly what it does. It detects objects and measures their distance. How distance is calculated. Here is where basic physics comes in. Radio waves travel at a constant speed, roughly 300,000 kilometers per second. That's the speed of light. So if you measure how long it takes for a radio signal to go out and come back, you can calculate exactly how far away the object is. For example, if the round trip takes 1,000th of a second, the object is about 150 kilometers away. Half of that time is the signal going out, and half is coming back. This relationship, time equals distance, is one of the most fundamental ideas behind all radar systems. How direction is found. But distance alone is not enough. You also need to know where the object is located. That is why AWACS uses a rotating radar system. The large dome you see on top of the E3 Sentry spins continuously. It makes about 6 full rotations per minute. As it rotates, it sends radar signals in different directions. By knowing exactly which direction the antenna is pointing when a signal returns, the system can determine the bearing of the detected object. This allows AWACS to scan the entire sky, creating a complete 360-degree view around the aircraft. Why the rotating dome matters. That rotating dome is not just an iconic feature. It is absolutely essential to how the system works. Instead of looking in only one direction like a fighter jet's radar, AWACS constantly updates its view of the entire airspace. Every rotation gives new data, so instead of a single snapshot in time, the system builds a continuously refreshed map of the sky. This means that if a target moves, the radar can track that movement from one rotation to the next, and if a new target appears, it is detected within seconds. Signal strength and object detection. Now here's something interesting. Not all radar reflections are the same. Some signals come back strong, some are very weak. The strength of the returning signal depends on several factors. One factor is the size of the object. Larger aircraft tend to reflect more energy. Another factor is the shape and material of the object. Metal surfaces reflect better than other materials. The system analyzes the signal strength to understand what it is detecting. A strong, steady return might be a large transport aircraft. A weaker, fluctuating return might be a smaller fighter. But the environment also plays a role. Rain, clouds, and even turbulence can affect the signal. Filtering out noise. The sky is not empty. There are all kinds of signals, reflections, and interference. Weather creates returns, birds can show up on radar, even the ground itself reflects some energy. So AWACS has to filter out this noise. This is where advanced signal processing comes in. The onboard computers separate meaningful data, like actual aircraft, from random or irrelevant signals. Without this filtering, the operators would see a cluttered screen full of useless information. Good filtering is what makes the system usable in real conditions. Detecting movement. One of the most powerful features of radar is detecting movement. By comparing signals over time, the system can determine if something is moving, and not just that, it can estimate direction and speed. This is often done using what is called the Doppler effect. When an object moves toward the radar, the reflected signal changes frequency slightly. When it moves away, the frequency shifts the other way. By measuring the shift, AWACS can tell not only where something is, but also how fast it is moving and in which direction. This turns simple detection into tracking multiple targets. AWACS does not just track one object, it can track many at the same time. Each target's signal is processed individually. Its position, speed, and direction are updated with every radar rotation. The system maintains a separate track for each object. This creates a dynamic picture of the entire airspace, where multiple aircraft are monitored simultaneously. Operators inside the E3 can see this picture on their screens. They can identify friend from foe, prioritize threats, and direct friendly aircraft. This ability to handle dozens of targets at once is what makes AWACS so valuable. Why altitude is a game changer. Here is one of the biggest advantages of AWACS over ground radar: altitude. Because the E3 operates high above the ground, it avoids many limitations that ground stations face. First, there are fewer obstacles. Mountains, buildings, and the curvature of the Earth do not block its view as much. Second, it has a much better line of sight. The higher you go, the farther you can see. Third, its coverage area is much wider. A single AWACS can cover an area that would require multiple ground radars. This dramatically increases its effectiveness, especially over oceans or rough terrain. Building a real-time map. All of this data comes together to form a real-time map of the sky. Not just positions, but movement patterns, speed changes, and trends over time. The system does not simply detect objects, it interprets what is happening in the environment. This is what makes AWACS so powerful. It gives commanders a clear, updated picture of the entire air situation. And that picture can be shared with other aircraft, ships, or ground stations through data links. So everyone in the battle space sees the same information. So, when you combine everything, transmitting radio signals, receiving reflections, measuring time to calculate distance, rotating the antenna to find direction, filtering out noise, detecting movement using frequency shifts, tracking multiple targets at once, you get a system that can monitor large areas continuously and reliably. AWACS does not rely on any single trick. It is the combination of all these principles that makes it so effective. And that is why, even decades after the E3 was first introduced, the basic concept remains extremely valuable. And that is how AWACS radar works, explained simply. It's not magic, it's physics, engineering, and smart system design working together. If you found this interesting, subscribe for more videos like this. I make deep dives into military aviation technology without the hype. And let me know in the comments, what system should we break down next? Thanks for watching. See you in the next one.